to prove an inequality using mathematical induction, we must use these three steps. First, we must prove that n equals 1, or the first term in the inequality is true. Second, we must prove that the inequality holds true for any value k. K is being any value that is within the that is any value that n can be, which is specified in the inequality. Third, we must prove that the inequality holds true for the next term after k, or the k plus 1th term.
Okay, let's start a new problem. This one is to prove n squared plus n is divisible by or a multiple of 2. And because we're doing the induction series, we first prove the statement holds true to the first term. This means that we replace n with 1. So first, n squared plus 1 equals what? So that'll just be 1 plus 1 equals 2, and we all know that 2 is always going to be divisible by 2. Or in other words, we can just write 2 times 1 equals 2. Next step is to assume that the statement holds true to any value of k. This is very simple because we're just plugging in k for n in the equation. So we do k squared plus k is equal to any number that's divisible or a multiple of 2. And we would write 2w. W meaning any whole number. Okay guys, our last step is to prove that the statement holds true for the next term, or in other words, the k plus 1th term. And in this sense, we just substitute the k plus 1 in our original equation, n squared plus n. So we do this, k plus 1 squared plus k plus 1. So after this, it's just simple enough. You just need to FOIL it out and then simplify. So that will just look like this. K squared plus 2k plus 1, and then you just add this on, plus k plus 1. And then simplify. K squared plus 3k plus 2. Now, I know this may seem weird and tricky that you might not be able to get the answer from this, that it might not look like a multiple or divisible by 2, but it is. You just need to apply it to the statement you had in the previous step. And by this I mean rearrange the equation so you can actually use it. So in this, we will just use k squared plus k plus 2k plus 2. Now remember, in your original equation, you made the statement k squared plus k equals 2w. You just need to substitute this into here because there it is. So you get 2w plus 2k plus 2. Now you see the similarities. All you have to do now is just factor the 2 out and then just put in your variables. And there you have it. It doesn't really matter what is in these parentheses right here, but as long as there's a 2 on the outside, it shows that it's a factor of 2 or a multiple and or divisible by it. And there you have it.
Alright, greetings. Welcome to Divisibility 101. A lot like inequalities, divisibilities follow the same 3 steps that we used to prove it. So the first step, we prove the statement is true for the first term, which is usually 1, or something that is provided in the original statement. Second term, the second thing you do is you assume that it is true for any number k, and we're going to use this statement for substitution in part 3. In part 3, we prove that it is true for the k plus 1 term, and that's how you prove it for divisibility.
I look at my Cartier out of control.
Alright, here's a practice problem we have. 9 to the nth minus 1 is a multiple and or is divisible by 8, assuming that n is bigger than 1, or any counting number. So here we have the first step where we prove that it works for the first term. So we plug in 1 for the n, so it becomes 9 to the 1 minus 1, which is equal to 8, which is definitely a multiple of 8. So we got it. Alright, so here's step 2, where we assume that the statement holds true for any value of k. So here we plug in k for the n, so it would be 9 to the k minus 1 equals 8 times w. Most people get confused, but you shouldn't worry too much about this w, because w is just a whole number, and it can be anything. All we care about is that it's a multiple of 8. This is the most important part.
We will also be using this statement in order to substitute for the third part in proving that the statement works for the k plus 1 term.
Alright, so here we are at the third step, where we prove the statement works for the next term after k, the k plus 1 term. So here we plug in k plus 1 for k, so it's 9 to the k plus 1 minus 1 equals 8 times any whole number. In this step, what we do is we add 9 and subtract 9. This does not alter the equation, and what we did this for is because we picked 9 because it is the base of the k exponent term. And we did this so we could work with it later. So after some grouping, it becomes 9 to the k plus 1 minus 9 plus 9 minus 1. And we did this so we could get this 8, which we were ultimately looking for. And in this step, we also took out a 9 out of 9k plus 1. This 9k plus 1 actually equals 9 times 9 to the k. Now what we did here is we factored out a 9, and from there we can make from here we can prove that this is 8 times a whole number, because back in step 2 we proved that 9 to the k minus 1 is actually 8 times any whole number. So after substituting that, 9 times 8, which times any whole number, plus 8, can actually be factored out. Once we take that 8 out, can be equal to this. Now the most important part that we got out of this is the 8. This number can be actually anything. So as you can see here, it can be any single number. All we care about is this 8.
Like my mind where I'm going, the women, the shorties know nothing about.
Okay, so this is the next problem that we're going to do, and we're going to prove that 2 to the power of n is greater than n using mathematical induction. And for this first step, I've already started it for you. You have to prove that the statement holds true for the first term. So you do n equals 1, and then we're going to substitute that 1 into the equation, so it becomes 2 to the power of 1 is greater than 1. And if that's true, which it is, that means we've solved that first step. This next one is we're going to assume that the statement holds true for any value of k. So I'm going to replace k in for the equation. So 2 to the power of k is greater than k. Overall, what we want to do is we want to prove that this statement is true, and this statement is proving that it holds true for the next term, which is k plus 1 term. And so that statement looks like this. It's 2 to the power of k plus 1 is greater than k plus 1. Okay, so essentially what we're going to do is we're going to do the work here and prove that it's going to equal this eventually. So my first step that I'm going to do is I'm going to multiply 2 by both sides. So it's 2 times 2 to the power of k, which is greater than 2k. Then what we're going to do is the transitive property. So essentially this is this becomes 2, because of this 2 times 2, it becomes 2 to the power of k plus 1, and is greater than, I'm going to distribute this to k plus k, which is the same thing. And if we're assuming that k is greater than 1, this is then greater than k plus 1. So that's the transitive property that we're using. So if this is greater than this, and if it's greater than this, then this whole statement can be true. And to make it look like this last statement here, all you have to do is the transitive property. And so it becomes this is greater than this value, which ends up looking exactly like your last step. So you've proven.
So knowing the 3 steps now needed to prove an inequality using mathematical induction, we're going to do a practice problem. So we're going to prove that n factorial is greater than 2n, given that n has to be greater than or equal to 4. So the first step is that we're going to prove that the statement works for the first term. The first term, according to our given information, is 4 because n has to be greater than or equal to 4. So therefore we're going to plug in 4 for n. So we have 4 factorial is greater than 2 to the power of 4. Now 4 factorial just means 4 multiplied by all the counting numbers down to 1. So 4 factorial then becomes 4 times 3 times 2 times 1 is greater than 2 to the power of 4. 4 times 3 times 2 times 1 is equal to 24, which is greater than 2 to the power of 4, which is 16. So we have proven the first step that the statement works for the first term. Okay, now the second step, we're going to assume that the statement holds true for any value k. In this step, we're just simply going to plug in this k back up here so that we can use it in our third step to prove that the statement will work for the next term. So by plugging in k, we come up with the statement k factorial is greater than 2 to the power of k. Of course, provided that k is greater than or equal to 4. Now we're going to use this information later and apply it to our third step using the transitive property. The transitive property is as follows. If A is greater than B and B is greater than C, therefore A is greater than C. And we have to multiply both sides in order to keep the inequality true. Now we can do this because we know over here that k has to be greater than or equal to 4, and any value greater than or equal to 4 that is added to 1 is positive, and therefore we do not need to be concerned about the sign. So we can simplify this now as k plus 1 factorial is greater than 2k times k plus 1. So now that we have this, we can assign each value in our statement a letter, where this is going to be A. Okay, so we're going to prove that the statement now holds true for the next, or the k plus 1 term. So we're going to plug in k plus 1 into our original equation, coming up with k plus 1 factorial is greater than 2 to the power of k plus 1. Now, we're going to have to go back to step 2 over here with our generated statement and rewrite it. So k factorial is greater than 2k. Now we want to transform this equation into this equation so that we can then use the transitive property to prove that this statement holds true. So k plus 1 factorial can be transformed from k factorial by simply multiplying by the next term, because k plus 1 factorial can be broken down into k plus 1 times k factorial. This is going to be b, and this value is going to be c. So assuming that a is greater than b, we now have to prove that b is greater than c in order to prove that a is greater than c. So we're going to set b greater than c. So 2k times k plus 1 is greater than 2 to the k plus 1. Now, we want to try to get both sides to have 2k so that we can cancel out the 2 to the power of k. 2 to the k plus 1 using exponential rules can be simplified to 2 times 2 to the k. Knowing that k is greater than or equal to 4 according to our original statement, we know that 2 to the power of k has to be a positive value, and then therefore we can cancel by dividing each side by 2 to the power of k without being concerned about messing up the sign. So now we are left with k plus 1 is greater than 2, which can then be simplified to k is greater than 1, which we know for sure, again, because k has to be greater than or equal to 4. So knowing that a is greater to b in this statement and b is greater than c, we can then conclude that a is greater than c, and that the statement holds true for any value k.